Alright, this will be video 2. So the last unit was more about compound stoichiometry and finding how many molecules is in every gram of a similar substance. This one's going to be reaction stoichiometry. We're going to start with a certain amount of one compound and find out how much of another compound it should make, or find out how much of another compound we need to add to produce a certain compound. Like I said, these can get pretty tricky, but it all follows a very similar format. So stoichiometry calculations, the first thing in your notes, can go between any substances in a reaction, reactants or products. So we can go between two products, or either reactant and a product, or one reactant and either product. Either way, we can always find it out. I really wouldn't pay attention to reactants or products going forward unless it's a conservation of mass problem. So stoichiometry helps us to find the theoretical yield, which we'll get into that into another video, and the maximum amount of product that should be made, hence theoretical. Theoretically, this much should be made. Not technically the actual yield, but you can only be found out through the experiment, which you'll do some of those in the lab for this unit. So mole ratios, if you really need to understand mole ratios, and good thing, these are pretty simple. You just got to look at the coefficients. So if we got 2H2 plus O2 yields 2H2O, what is the mole ratio between hydrogen and oxygen? Well, just look at the coefficients. You have 2 moles of hydrogen for every 1 mole of oxygen. So it's a 2-to-1 ratio. You can either write it like that, like you would a ratio in your math class, or I can do it like a fraction, 2-to-1. Either way, you'll probably end up using it more like this when you're doing math, but I will take either kind of ratio. So the next one is going to be hydrogen to water. So we get 2 hydrogens and 2 H2Os. It's a 2-to-2 ratio. Once again, you could write it as 2/2. And this one, you could simplify it. You certainly do not have to go 1/1. The math will work the same way, so you don't have to simplify it, but either one of those answers would technically be correct. So for 3, oxygen to water. You have 1 oxygen to 2 waters. So 1/2 or 1/2. You really wouldn't put that into a decimal form because of dimensional analysis, so leave it as 1/2 or 1/2. Water to oxygen, going back the other way, 2-to-1. 2-to-1. So I hope you're getting the hang of these. They're very, very easy. Then water to hydrogen, 2 waters to 2 hydrogens. So 2-to-2. Once again, 2/2. Or you can simplify it if you wanted to 1/1. Either one of those works. So let's go on and actually apply these. So use the balancing equation for the synthesis of water to determine how many moles of water would form if you begin with that many moles of oxygen gas. So like we always do, start with your given. 32.38 moles of oxygen gas. And so here, like we did last unit, we're going to start with moles of O2. We're going to go to find our destination, moles of water. So we start with our given. Draw your grid. Remember, if we've got moles of O2 in the top left, we've got to have moles O2 in the bottom right. And our destination in the top right. So here we just do the mole ratio. We need moles of O2. Right there is going to be 1. So 1 mole O2 going to moles, sorry, that should be H2 at the top, it should be H2O. 2 moles H2O. So there's our 2-to-1 ratio. So your math would be 32.38 times 2 divided by 1. That should equal 65.6 moles of H2O. So that's going to be the easiest problem you'll ever have to do. One-step dimensional analysis. Let's move on. This thing is coming back again. You've got to remember it because you're going to be using 2, sometimes 3 of these. So remember, if we're starting in grams, or anything is in grams, we're going to use the molar mass to convert to moles. You always, always, always convert to moles, still. So in this unit, we're going to convert to moles, do a mole ratio, and then convert from moles. Remember, if we're going to any one of our particles, we're going to use Avogadro's number. And now, if we're going to volume, 22.4 if we're going to and from volume. Make sure you understand this chart, be able to reproduce it on any type of assignment. How many grams of H2O can be formed by reacting 5 grams of H2O? So we're starting with grams of H2O, and we're going to end in grams of H2. Actually, just kidding. We're going from grams H2 to grams H2O. Got to read the question. So we're going to start with 50 grams of H2. So the first thing we got to do is convert grams H2 and 2 moles of H2. So you didn't do that. If we go back, we're going from grams to moles, we're going to use the molar mass of H2. So 1 mole for every 2.02, because remember H2 is diatomic, grams of H2. Part 2, do the mole ratio bridge, or just the mole ratio as I'll call it. You have moles of H2 on top, so you got moles of H2 at the bottom. And then we're going to go to, since we're ending up in H2O, we're going to go to moles of H2O. So we've got 2 moles from that coefficient of H2 and 2 moles from the coefficient of H2O. Once again, if you really wanted to, you can simplify that to 1 over 1, but it doesn't matter. So finally, we convert away from moles in step 3. Once again, we got moles of H2O here, we've got moles of H2O here. We're going to end up in grams of H2O. We have the 1 mole here, and if we're going from moles to grams, we're using molar mass. It's going to be 18.02. And just do the math like normal. 50 times 1 times 2 times 18.02. Hit enter. Divide, parentheses, 2.02 times 2. Make sure you put this in your calculator right. You should get 446 grams of H2O. There you go. All right, so let's move on to the next example problem. How many grams of sodium chloride can be formed in a synthesis reaction with 30 grams of chlorine gas? So we're going to go from 30 grams of chlorine gas, or that's diatomic. We're going to get to grams of sodium chloride. First, you're going to need to write your equation, which you guys should be able to do by now. It's Cl2 plus 2Na yields 2 NaCl. You've got to have that balanced equation, otherwise your coefficients will be off. So like always, you start with your given, 30 grams of chlorine. And first step we always got to do is convert to moles. So grams of chlorine, 2 moles of chlorine. Moles of our given. 1 mole of chlorine is 70.9 grams. Oops, there's 2 grams there. Oh well. From there, we do the mole ratio. So we go moles of chlorine. Now we get to our destination, which is going to be moles of sodium chloride. We've got 1 mole of chlorine gas to every 2 moles of sodium chloride. Then we convert away from moles, so moles of sodium chloride. We're converting to grams of sodium chloride. So 1 mole of sodium chloride equals 58.44 grams of sodium chloride. Do that math, and you get 49.46 grams of NaCl. Once again, make sure you're putting these in your calculator correctly. Don't just take my word for it. So the next problem, we're starting with 45.7 grams of lithium iodide. So grams of lithium iodide. We're going to grams of bromine. Bromine is another one of those diatomics. So first you're going to need the balanced equation, which is going to be Br2 plus 2Lii, lithium iodide, to form lithium bromide, 2 lithium bromides, and an iodine, which is another diatomic. So you start with your given, like always, 45.7 grams. And first thing you got to do is convert to moles. So grams of lithium iodide to moles of lithium iodide. 1 mole of lithium iodide is 133.84. Remember, these are molar masses. Next step is the mole ratio. So you have mole of, lithium iodide, 2 moles of bromine. So then we have 2 moles lithium iodide to 1 mole of bromine. So you can see how we can go between 2 different products to find out how much of one product we can react with how much of another product. From there, we go away from moles. So we have 1 mole of bromine to grams of bromine, which would be 79.9 grams of bromine. So you do 45.7 times 79.9 divided by, parentheses, 133.84 times 2. That should get you 13.64 grams of bromine gas. I hope you guys have figured out that there is a pattern here. I'm going to go ahead and give the pattern. I want to see these in your notes. So you have given here that you have a conversion factor then you always have 1 mole given. Then you have coefficient of your given to coefficient of your destination to 1 mole of your destination to your conversion factor of your destination. Your conversion factor is molar mass 22.4 or Avogadro's number. So if you write this down, the rest of the class is pretty simple. So let's go ahead and go back. You'll see that this will follow the exact same pattern. But how many molecules of hydrogen gas? So I start with grams of nitrogen gas, once again another diatomic, to form molecules of hydrogen gas, another diatomic. So you got to get the right equation. It's going to be 3H2 plus that's 2 and H3. So once again, you start with your given, 0.334 grams of nitrogen gas. So we're given grams, we're going to use the molar mass of nitrogen gas, which is 28.02 grams of nitrogen gas. 1 mole given, so 1 mole of nitrogen. You're going to do your mole ratio. So we've got moles of our given going to moles of our destination. So coefficient of our given is nitrogen, that's a 1. Coefficient of our destination is hydrogen, that's a 3. Then we convert away from moles. It's 1 mole of our destination, so 1 mole of H2. And we're going to molecules. H2, this is another conversion factor. We're going to molecules, so we're going to use Avogadro's number, 6.02 E23. Let's do the math. Once again, make sure you're using your E's. That should get you 2.15 times 10 to the 22nd molecules of H2. And please make sure you're keeping track of those units, guys. Okay, next one. How many moles of water can be potentially produced? Whatever. Go from grams of O2 to moles of H2O. So once again, you're going to need the equation. 2H2 plus O2 yields 2H2O. So you start your given. This time you're in moles, so you can get it, or not moles. So you're given 5.6 grams of O2. We're in grams, so we're going to use the molar mass of O2, which is 32 grams O2, to 1 mole O2. Next step, conversion factor, coefficient of our given is 1. Coefficient of our destination is 2. Now here's the trick. This time we're going to moles. If we're going to moles, we can end right there, because anything else would be converting from moles, but it says we can stop at moles, so we just stop it right there. Do your math, you get 0.35 moles H2O. So that one was a little bit short. Anytime you see moles, you should know you've got a shorter grid coming up. Okay, the next question, if you read it, you might see this STP stuff. Don't be distracted by other words in the question. Keep your focus on what we're doing with this unit. STP means nothing to you right now. It'll mean something next unit, but right now it doesn't mean anything. All you know is you've got moles of nitrogen. You're trying to find volume of gas. So you've got 0.0580 moles of nitrogen monoxide. It's NO. This is how much volume is that? Well, you always do 1 mole down here. And it says volume. Remember, our volume is liters. And we going between moles and liters. This is the first time you may have seen this. Is 22.4 liters in every mole. This is just showing you the calculation using volume. Let's do the math like always. 1.30 liters of NO. Okay, that one was simple. Let's keep on going. How many atoms of O2 are in every 45.6 liters? So we are starting in 45.6 liters. We always convert that to moles, so 22.4 liters are in every 1 mole. Then for moles, we'll go to atoms. So 1 mole going to atoms, so we know we're going to use 6.02 E23 atoms of O2. Since we're going to O2, you do that math and you should get 1.23 times 10 to the 23rd atoms of O2. This goes back to unit 1, just using a new conversion factor. And finally, how many grams of CO2 are in 20.3? This is just using the same conversion factor, but going to grams instead of molecules. So you're turning right at mole instead of turning left. So you're going to start with your given, 28.3 liters. There are 22.4 liters in every 1 mole. And in every 1 mole, we're going to grab the CO2, so we've got to use the molar mass in this one, which turns out to be 44.01. That will give you 55.6 grams of CO2. So once again, you've got your grids. Make sure you understand how to use them. We will get a lot of practice for dedicating a whole day to this. So be prepared to do a lot of math when you come to class. That's all for